The summer of 2025 brought a chilling discovery to the windswept beaches of St. Paul Island in the Bering Sea. For generations, the Algae community there has lived in rhythm with the ocean, harvesting fur seals and fish. But this year, the tide brought death. Dozens of northern fur seals, majestic, intelligent marine mammals, washed ashore, their bodies convulsing in their final moments, or already still. For the first time in history, scientists conclusively linked these deaths not to starvation, entanglement, or viral disease, but to saxitoxin, a potent neurotoxin produced by microscopic algae. In the icy waters of the Arctic, where such toxic blooms were once a rarity, a new biological reality has taken hold. This tragedy is not an isolated incident. It is a warning siren from our warming oceans. From the sun-baked coast of Southern California to the drinking water intakes of Lake Erie, a microscopic menace is rising. Climate change is not just making our waters hotter, it is fueling the proliferation of paralytic shellfish toxins, turning the base of the marine food web into a poison chalice. Today, we are going to dive deep into the complex, often terrifying and fascinating science behind how warming waters are supercharging toxic algal blooms, the mechanisms driving their expansion, and the cutting-edge technology humanity is deploying to fight back. To understand the threat, we must first understand the weapon. Saxitoxins, often abbreviated as STXs, are among the most potent natural neurotoxins known to science. Produced by specific species of dinoflagellates in saltwater and certain cyanobacteria in freshwater, these toxins are chemically stable, heat-resistant, and tasteless. This is a crucial detail for anyone who enjoys seafood. You cannot cook them out of a clam, and you cannot freeze them out of a crab. The toxin survives the pot and the freezer. When ingested by humans, usually through contaminated shellfish, saxitoxins cause paralytic shellfish poisoning, or PSP. The mechanism is terrifyingly efficient. The toxin binds to voltage-gated sodium channels in your nerve cells. Think of your nerves like electrical wires. The sodium channels are the switches that allow the current to flow. Saxitoxin effectively plugs these channels. It prevents nerves from firing instructions to muscles. Symptoms can appear within minutes. Phase 1 involves a tingling or burning sensation, often described as pins and needles, in the lips, tongue, and fingertips. As the poisoning progresses to Phase 2, numbness spreads to the arms and legs, and movement becomes uncoordinated, a condition known as ataxia. In Phase 3, the paralysis reaches the chest muscles. Without medical ventilation, the victim suffocates while remaining fully conscious. For marine life, the consequences are equally devastating. But why is a warming planet making this ancient biological weapon more prevalent? Perhaps the most alarming shift is occurring in the Arctic. Historically, the waters of the Chukchi and Bering Seas were too cold to support massive blooms of Alexandrium catenella, the primary saxitoxin producer in North America. The cysts, which are essentially the dormant seeds of these algae, would lie on the seafloor, waiting for a warmth that rarely came. But as sea ice retreats and water temperatures climb, the Arctic is undergoing a process scientists call Atlantification. Warmer water from the Atlantic and Pacific is pushing north, carrying toxic algal cells with it. In recent years, scientists have mapped a massive cyst bed of Alexandrium stretching across the seafloor near Alaska, one of the largest ever documented globally. This is essentially a dormant giant. As bottom waters warm, these cysts are now hatching in synchronized mass events. The open water, free of ice for longer periods, provides the sunlight needed for these hatched cells to photosynthesize and multiply exponentially. In temperate regions like Puget Sound in Washington and the Gulf of Maine, climate change is expanding the seasonal window for blooms. In the past, these toxic events were restricted to late spring or early summer. Now we are seeing blooms initiating earlier in the spring and persisting into late autumn. The mechanism is straightforward. Warmer springs wake up the dormant cysts earlier, and warmer autumns prevent the water from cooling down enough to kill off the bloom, allowing the algae to produce toxins for months longer than usual. Furthermore, in 2024 and 2025, California witnessed a disturbing new trend called dual blooms. Historically, the region battled either pseudonychia, which produces domoic acid, or alexandrium, which produces saxitoxin, separately. Now, overlapping favorable conditions are allowing both to bloom simultaneously. Marine wildlife rescue centers are becoming overwhelmed because sea lions are coming in with cocktails of toxins in their systems, which complicates treatment and significantly increases mortality rates. Here is where the science gets incredibly nuanced, and it creates something of a biological paradox. One might assume that warmer water simply equals more toxin. However, the biological reality of gene expression is more complex. Recent molecular studies on alexandrium, specifically looking at the SXT genes responsible for toxin production, have revealed something counterintuitive. These algae often grow fastest in warmer water, around 16 to 20 degrees Celsius. However, individual cells often produce more toxin per cell when they are under cold stress or suboptimal temperatures, like 12 degrees Celsius. The hypothesis is that when growth slows down due to cold, the cell's internal machinery has excess energy, specifically arginine, that gets shunted into toxin production rather than cell division. So if cold makes individual cells more toxic, why is warming the problem? The answer lies in biomass. Even if individual cells are slightly less toxic in warm water, the sheer number of cells explodes. 1 billion moderately toxic cells are far more dangerous than 1 million highly toxic ones. Additionally, warming drives range expansion, allowing the algae to exist in places they never could before, like the Arctic. We are also seeing the rise of generalist species. While Alexandrium prefers temperate waters, other species like Gymnodinium catenatum act as warm water lovers. They thrive in heat between 22 and 28 degrees Celsius. As oceans warm, Gymnodinium is expanding its range in Asia and Europe, replacing cold water species and bringing saxitoxins to new shores. For decades, the narrative of saxitoxins was strictly a saltwater story. But recently, the script flipped. In Lake Erie, which is notorious for its green, slime-like microcystis blooms that produce liver toxins, scientists detected saxitoxins. The mystery was, who is making it? In December 2025, researchers from the University of Michigan finally cracked the case. The culprit is Dolichospermum, a type of cyanobacteria. This organism thrives in a specific climate scenario: warming waters combined with low ammonium levels. This discovery is a game-changer for freshwater management. Most monitoring focuses on microcystin. If saxitoxins are also present, water treatment plants need completely different protocols to ensure safe drinking water for the millions of people who rely on the Great Lakes. The human and economic toll of these shifts is profound. For indigenous communities in Alaska, the ocean is a grocery store. Clams, mussels, and crabs are staples of subsistence diets. But the unpredictability of modern blooms has turned harvest into a game of Alaskan roulette. While mussels can flush toxins out of their system in weeks, butter clams, scientifically known as Saxidomus gigantea, are notorious for holding onto saxitoxins for up to 2 years. A bloom that happened in 2023 could still kill a harvester in 2025. This leads to cultural erasure. When elders cannot teach youth how to harvest safely because the old signs, like seasonality, no longer apply, cultural transmission is severed. Economically, the fisheries industry faces losses in the millions annually due to closures. In the Pacific Northwest, saxitoxins accumulate in the viscera, or guts, of Dungeness crabs. If levels are high, entire commercial seasons are delayed or canceled, devastating coastal economies. Aquaculture farmers, who rely on clean water, are forced to hold product for months, increasing costs and risk of mortality. However, humanity is not standing still. We are deploying an arsenal of high-tech tools to detect these invisible assassins before they strike. One of the most impressive technologies is the environmental sample processor, or especially, this is essentially a lab in a can, an underwater robot that sits on the seafloor. It sucks in water, extracts DNA, and runs a generic test for algal species in situ. New sensors developed by NCCOS for 2025 now allow these robots to detect the toxins themselves, not just the algae cells, transmitting real-time data to scientists on shore. In Norway and the US, researchers are taking a different approach using submersible microscopes coupled with artificial intelligence. These devices take holographic photos of every particle in the water. An AI algorithm trained on thousands of images identifies toxic species like Alexandrium in milliseconds and alerts authorities. This eliminates the days-long delay of sending water samples to a manual lab. We are also looking at nature-based solutions. A surprising ally has emerged: sugar kelp. Studies have shown that growing kelp alongside shellfish can mitigate blooms. The kelp competes for nutrients and may even produce allelopathic chemicals that inhibit the growth of toxic dinoflagellates. Integrated multi-trophic aquaculture is currently testing whether these kelp curtains can effectively shield oyster farms from toxic blooms. Looking ahead to 2050 and beyond, climate models paint a stark picture. We expect a poleward shift, where the band of habitable water for temperate species like Alexandrium continues to move north. By 2100, the Arctic Ocean could host annual, high-intensity blooms, fundamentally altering the Arctic food web. Conversely, some tropical waters may become too hot for certain dinoflagellates, potentially reducing PSP risks in specific equatorial zones, though likely replacing them with other heat-tolerant toxin producers. We must also consider synergy with acidification. As oceans absorb CO2, they become more acidic. Early research suggests that lower pH may enhance the toxicity of some Alexandrium strains, meaning future blooms could be more potent even if they aren't larger. The rise of saxitoxins is a silent, invisible symptom of our changing planet. It challenges our ability to feed ourselves from the sea and threatens the biodiversity of our oceans. However, the path forward is illuminated by science. Through the combination of indigenous knowledge monitoring changes in animal behavior, cutting-edge technology like AI and robotics, and global carbon reduction, we can adapt. The ocean is changing, and to survive, our relationship with it must evolve too. We can no longer take the safety of the harvest for granted. Vigilance is the new price of seafood.